Okay, so thank you for the introduction and thank you for the invitation. It's a joy to be here. I love to be in Singapore and discussing and interacting with this community. It's been truly a beautiful week, full of beautiful, interesting talks and ideas. So my talk is about Stein's method and some application, some connection that's been established, that has been already evoked in several talks between Stein's method and methods of infinite dimensional Gaussian analysis. So this was my entry point in Stein's method around 10 years ago. So we realized together with my friend, which is not here, Ivan Urdan, that there was a connection between Stein's method and some tools of Gaussian analysis that are known as the Malявin calculus of variation. And so several results have been proved. And what I'm going to describe today is an application of these methods. So it's a connection between Malявin calculus and Stein's method in a Gaussian setting to problems that arise in stochastic geometry, but not the kind of stochastic geometry that Jukic has been discussing with us about random graphs or discrete structures, but more like the geometric object that arise from random fields, so random function defined on some spaces. And so this is connected with several works, at least 4 works, with several co-authors. So there is Ivan Urdan appearing in 2 of them, and then there is Domenico Marinucci and Igor Wigman from Rome and London. And there is a common co-author among all those, Federico Dalmau from Montevideo, and then there is a common co-author on these 4 works, is a young, very strong lady, Maurizia Rossi. Now she's in Rome, and she's a very interesting researcher that knows many things about Stein's method, Gaussian analysis, and connection limit theorems, and differential geometry. And so I think it's remarkable, new and young researcher that you should just write down on your notes as a name, someone to invite somewhere in the future. Okay, so the starting point, as I was saying, is that maybe in 2009, more or less, together with my friend Ivan Urdan, we discovered that there was a very powerful and natural connection between Stein's method for probabilistic approximation, so at the time we were really focusing on normal approximations, and another collection of tools of infinite dimensional analysis, which is known as the Malявin calculus of variation, which can be really described as the infinite dimensional differential calculus, like a generalization to infinite dimension of a usual calculus. And this calculus of variation has operators that act on functionals of Gaussian fields. And more generally, one can define a Malявin calculus for more general objects like random measures, Poisson measures, but we were really focusing on Gaussian fields. And the connection between Stein's method and Malявin calculus that make the interaction between the two so natural is that both use in a very intensive way integration by parts formula. So we saw many of them in the previous talk in a one-dimensional setting or in a finite dimensional setting. So it's really a very natural tool to deal with Stein's method is to use finite dimensional integration by parts formula. And if you're a bit into Malявin calculus, you know that at the core of Malявin calculus are infinite dimensional integration by parts formula. So they combine very well together, and they give bounds that can be used in several applications. And so let me just, before going to the main part of my talk, let me just rephrase or say again something that has already been observed, for instance, in the talk by Guillaume 2 days ago. So as we know, in this room, every one of us knows that normal approximation, for instance, using Stein's method for normal approximation requires us to bound uniformly expressions of this type, where capital F is a random variable that you would like to compare with a Gaussian random variable. And G is a function that arises as the solution of the Stein equation associated with a given test function that can be smooth or non-smooth. So what happens in Gaussian analysis is that you can really deal with non-smooth test functions. So you can directly deal with distance total variation, for instance, without major problems or major differences. And so what happens, and already this was observed by Guillaume in his talk, is that one can transform by using tools. So if you assume that capital F is a random variable that lives on a Gaussian space, and is a sufficiently smooth transformation of a Gaussian field in infinite dimension, then you can transform exactly this expression in the following way. You can transform this expectation of f, g of f, into the expectation of g prime of f times this inner product of Malявin derivatives, and where one of the Malявin derivatives involves the inverse of the Ornstein-Uhlenbeck semigroup. So I'm not going to use it, and I'm not going to really define these objects, but so it turns out that this quantity here is really amenable to analysis. In several situations, it's really amenable to analysis. And let me tell you that now, if here so this random variable is in general not measurable with respect to the sigma field generated by f. Now, if you take this random variable and you take the conditional expectation with respect to f, and you divide by the variance of f, then what you have is the Radon-Nikodym density of the zero bias transform associated with a distribution of f. Okay, so there is a direct connection. And so one of the contributions of our research has been that, okay, if you represent this density as a conditional expectation, and if you remove the conditional expectation, then inside you have an expression which is really amenable to analysis, whereas the conditional expectation is very difficult to compute in the situations we're interested in. Okay? And then, okay, so this is an operator, L minus 1, that's been described in the previous talk, at least by Guillaume. And as you can imagine, the analysis becomes even, I mean, this object is even more amenable to analysis whenever you deal with a function which is an eigenfunction of this operator, L minus 1 of f. So these eigenfunctions have a name. These are elements of what one calls the Wiener chaos. And what I would like to point out is that among the contributions of this connection between Stein's method and Malявin calculus is really a further and fully quantitative understanding of the asymptotic structures of random variables that live on the Wiener chaos. So I will tell you why these Wiener chaotic random variables are quite important, but the main topic of my talk will be to show that they appear in a very natural and unexpected way in models of stochastic geometry. And indeed, so this characterization of the asymptotic structure of Wiener chaos that we have been able to obtain by using Stein's method, among other tools, so now it is reflected in the asymptotic properties of some geometric models, and it wasn't clear at all that these models had this connection, very tight connection with Wiener chaos. So let me describe to you a little bit what Wiener chaos is about, and so what kind of random variables we are looking at. So Wiener chaos is an infinite dimensional generalization of Hermite polynomials. That is, if you start with a one-dimensional Gaussian random variable, and then you look for the family of orthogonal polynomials associated with this one-dimensional distribution, you have the Hermite polynomials. Now, if you do the same operation for a finite-dimensional Gaussian vector, you obtain some proper family of Gaussian polynomials, of generalization of Hermite polynomials according to the covariant structure of the vector. And then if you can try to do the same in infinite dimension, what you obtain is a collection of orthogonal spaces, and these orthogonal spaces are called the Wiener chaos. It's the Wiener chaos associated with the given field. So this is a very general construction. You consider a generic Gaussian field with separable, meaning that it is generated by countable collection of Gaussian random variables. I mean that the Gaussian space is generated by countable collection. This is really generic. It can be just Brownian motion or whatever you have in mind. And then for every integer q, you define P of q to be the L2 closure of the vector space, which is generated by polynomial transformations on the field such that the degree of the polynomial does not exceed q. Okay, so you take all polynomial transformations of this Gaussian field, and you just fix the order of the degree of the polynomial to be not more than q. Of course, if you do something like this, you obtain a order sequence of spaces, pq is containing pq plus 1. What you can do, you can orthogonalize them, like in Gram-Schmidt orthogonalization by an infinite dimensional setting. So in this way, you can define a collection of orthogonal spaces, C of q bigger than 0. And so the first one is just the real numbers, the constants, and then you define C of q to be P of q intersection the orthogonal of P of q minus 1, where the orthogonality in the sense of L2, right? This is exactly an orthogonalization. This is what you do when you build Hermite polynomials, for instance. It's exactly what you do in a one-dimensional setting, and here you do it in an infinite dimensional setting. Then, for all the nice properties of the Gaussian distribution, it is easy to show that polynomial transformations are dense in square integer random variables, and I approximate square integer random variables with polynomials up to any degree of precision. So meaning that actually this is an orthogonal sequence of spaces of L2 that decompose the whole spaces of L2 of square integer random variables that are measurable with respect to G. Okay, so this is an infinite decomposition, and this means that if you have any random variable, which is a function of a Gaussian field, and that is square integrable, then you can represent it as an infinite orthogonal series of projections on this orthogonal space, of elements of chaotic spaces. And so this space C of q, as I was anticipating, so I'm not going to prove this, but this space C of q is actually the eigenspace associated with the eigenvalue minus q of L. So there was L minus 1, and this is the operator L, which is the generator of an Ornstein-Uhlenbeck semigroup, and this is called the Q Wiener chaos of G. Okay, so this space of orthogonal random variables can be used to decompose any square integrable random variable of any Gaussian field. So it's a very general construction that, and what happens is that one can, very often in application, we really see one in a while, one is interested in understanding the fluctuation, asymptotic fluctuation of sequences of random variables that live in a fixed Wiener chaos. For several reasons, this is very often a good idea to start studying the fluctuation of a generic random variable by looking at the fluctuations of the projection of these random variables of a given Gaussian field, then to glue things together in some way, right? And so this can be done admirably well by using Malevin calculus and Stein's method together in a quantitative way. So I'm not going to write bounds, I'm going to write one on the blackboard. But so there are, and what happens if you apply this kind of integration by parts formula to random variable in a Wiener chaos, you observe something that has already been described in the same way. I prepared the slides before, but before you gave the talk, but it is like, because there is a rigid asymptotic structure. So some part of the rigidity was described by Guillaume, and some of it is already available. So for instance, so the first thing I would like to say is a result which is not really proved by Stein's method, but it's a very beautiful result. So you fix an order Q, so you take, for instance, Q equal to 2. So Q equal to 2 is basically, these are polynomials of order 2, the closure of the space of polynomial transformation of order 2, orthogonalized, and then applied to any Gaussian field. So you fix an order Q bigger or equal to 2, and you consider a sequence of random variables that lived in the Wiener chaos of order Q. And then you're interested in understanding what happens. Okay, let's take unit variance in order not to have trivial cases, and you would like to understand something about the limiting behavior of this sequence f of k. So there is a very nice result, 2013, by Ivan and Guillaume, that tells you that automatically, if you have a random variable that lives in a Wiener chaos, then the limit, unless you are converging to 0, which you cannot because we are assuming unit variant, then the limit has to have a density. Okay? So basically means that if you can reduce the asymptotic fluctuations of one of your probabilistic models based on a Gaussian noise to a projection of a single Wiener chaos, then automatically you know that your limit has to have a density with respect to the Gaussian distribution. So this is an example of this rigidity. Then there is something we discovered in 2005, then we studied quantitatively by using Stein's method, which goes as follows. So now, suppose that very often you are interested in understanding when a sequence of random variables within a Wiener chaos converges to a Gaussian distribution. And this happens, so we proved that this happens, so such a sequence converges to the Gaussian distribution if and only if the fourth moment of the sequence converges to the fourth moment of the Gaussian distribution. We are assuming unit variance here. And so one of the first applications that I developed of Stein's method together with Ivan was to have a quantitative version of this result. And this quantitative version tells you the following. So remember, so let's fix, so f is an element of CQ. It is a center random variable always, and the variance is 1. And then what we basically proved is that if you take any variances, any distance that you might be interested in, total variation distance, Wasserstein distance, Kolmogorov distance, bounded Wasserstein distance, whatever, and you're looking at the distance between the distribution of f and the distribution of n01 random variable, then this is basically bounded by a universal constant. It changes with T of v, it is always less than 4, then the square root of the expectation of f to the power 4 minus 3. Okay? So this is a bound that is proved exactly by using this integration by parts, Stein's method. And okay, one can prove that this is always positive. And so this, of course, gives much more information. It tells you in which topology this convergence takes place. It takes always place in total variation, which is completely not clear at the beginning. And also here the constants do not depend on the order of the chaos, so you can let the order of the chaos move. So there are much more information that is contained here. And another thing that we have studied also quantitatively by Stein's method is the following phenomenon. If you have a sequence of random variables, each of them living in a chaos, possibly different chaoses, and if you can prove that their covariance converges to something, and then they separately converge to the Gaussian distribution, then you know automatically that the convergence to the Gaussian is joint. Okay? You don't have to control anything more than the covariance and the convergence of the single component. So this is another example of rigidity. And then there is another result that we were never able to connect properly with Stein's method, is that if you have sequences of random variables that live in chaoses, so one in the chaos of order P and the other one in the chaos of order Q, then these two random variables are asymptotically independent irrespective of the limit distribution, if and only if the covariance of the squares converges to 0, okay, which is quite a feat, because this, of course, is a necessary condition for independence, but not sufficient in general, right? And in any case, this is the asymptotic behavior of these chaotic random variables is not really understood. For instance, one cannot characterize all the possible limits of chaotic random variables when you go outside the chaos of order 2, and there are so many open questions. So now what I would like to do, so this is an overview of what have been done by combining Markov calculus and Stein's method. What I would like to do is to present you a situation, yeah? Yeah. Yes, right. Right, yes. This is a result that does not depend on the Gaussian field, the underlying Gaussian field. This is the chaos, you can take any variable in a chaos generated by a generic Gaussian field, and this result is always true. This is what I mean. I mean that the underlying Gaussian field does not play any role. It is actually you need the Gaussian field can be generated by a countable sequence of IID Gaussian random variables. You can always put yourself in this situation. Okay. So remember, so now I would like to show an example where this use of limit theorems connected with Wiener chaos arise in an unexpected way, and was actually able to explain a phenomenon that was observed in some papers, which are mathematical physics and other analysis. So what I would like to do is the following. So I'm going to look at some problems of stochastic geometry that are related with random functions. And actually the random functions I'm looking at are random eigenfunction of a Laplace operator of some fields. Okay, so we are very observing at least 2 talks in this conference that is a good thing to study the Laplace operator. This gives much information about the given manifold. So we are focusing on very specific and simple manifolds. But what we are doing here are studying the asymptotic behaviors of geometric features associated with random eigenfunction of a Laplace operator of a given manifold. And why should one be interested in dealing with this random eigenfunction is that because one could look at this random eigenfunction as a sort of a generic eigenfunction. So there are a lot of conjectures and different problems related to the geometry of eigenfunction of a Laplace operator of manifolds. You cannot study them by just focusing on one specific deterministic eigenfunction on a specific manifold. It's too difficult. And so what people do in analysis in differential geometry is very similar to what people do in statistical physics. They generate generic random objects by using the Gaussian distribution. So, and very often the things that one can prove by using this generic random eigenfunction of a Laplace operator is consistent with a number of conjectures in the domain. So I'm not going to go in this direction, but you should think this as a sort of weakening of proving a result for these random functions is a sort of a weak version of corresponding open problems for deterministic eigenfunctions. Okay. And so, in the first model I'm going to look at is a model by Michael Berry, which is not the Berry of the Berry-Scene, which is another Berry, which is a very well alive and kicking mathematical physicist from Bristol, but it's extremely famous and illustrious. And so, in 1977, he proposed a model for a generic eigenfunction of the Laplace operator on R2. Okay, you can do the same in any Euclidean space, but not R2. And so, this is called the Berry random wave model, which is associated with E, and E is going to be the eigenvalue of the Laplace operator. And so there are several ways of defining this model, but the simplest is to just to declare that your Berry's random wave model with parameter E is the unique, because you can prove it is unique. So it's a centered Gaussian process indexed by the plane, by R2, which is isotropic. This means that the distribution of this field is invariant with respect to rigid motions of the plane. You can rotate, you can translate, and we obtain always something that is like this. And then you require that this, with probability 1, this field is a solution of this Helmholtz equation that is the Laplacian of BE plus E times BE. This dot is just usual scalar multiplication, is equal to 0. So it's an eigenfunction with eigenvalue minus E of the Laplace operator. Okay, so you declare this. Of course, this, you can re-express this in terms of all these requirements can be expressed into requirements about the covariance function of the field B of E, and the general theory of isotropic Gaussian processes that you can, for instance, find in the book by Adler and Taylor, tells you that necessarily the covariance function of this process can have there's just one process with these properties, and it has this representation. So it is such that the covariance between B of X and B of Y is the integral, with respect to the uniform measure on the unit circle, of the exponential of I square root of E, X minus I, Z. And then by rotational invariance of the uniform measure on the circle, actually this quantity only depends on the Euclidean distance between X and Y. It can be expressed in this form, so J0 is the Bessel function of order 0, of the first kind of order 0, computed in the point square root of E times X of minus 1. And of course, this representation confirms the fact that the process is isotropic, because everything depends only on the distance between X and Y, and then any rigid motion of the plane would not modify the distribution of this process. Okay? So this is an infinite dimensional Gaussian process, because we will see some finite dimensional Gaussian process. So I'm not really going into details of this, but this is a sort of universal object. You should think about this as a sort of universal object. That is, if you take a generic manifold, there are several models that have been proposed in order to generate a random eigenfunction of that Gaussian eigenfunction of generic manifold. For instance, one of them is called, which is quite well known, is called a monochromatic random wave. So this is modeled by Zeldich. I'm not going to give a definition. But what happens for most of these models is that if you look locally at them, it is in a point where you can identify the manifold very close with the tangent plane, then they basically look like the Berry random wave model. So more precisely, this Berry random wave model emerges as a local scaling limit in a number of Gaussian field on two-dimensional manifolds that are also approximately eigenfunction by Laplace operator on the manifold. Okay? And there is something even more. There is a conjecture that has been already formulated in this paper by 77, which is not clearly formulated at least not to my sense or to my knowledge, but basically it tells you that if you look locally at the behavior, the deterministic eigenfunction, and you do that when you let the eigenvalue, the energy, go to infinity, then the behavior, the deterministic eigenfunction on any manifold, it's very close to the behavior of the Berry random wave model, at least as far as for concerning level sets, maybe the zero set of this process. Okay, so the message is that this is a universal object that appears in many applications as a local scaling limit of random fields. And so what we are interested in, which is related to a number of conjectures to the geometry of this eigenfunction of the manifold, is to a very specific level set of this. This is the zero set. So we are looking at the zero set of this object which is defined on the plane. So, we are interested in understanding what happens to this zero set whenever we let the eigenvalue E go into infinity. Okay, so let me show what I have here. So this is a very smooth process, first of all. If you have a covariance of this type, then this process will class C infinity with probability 1. And also, this process has some very nice properties. For instance, there are no points of the zero set on which the differential is equal to 0 with probability 1. This is due to the form of the covariance. And so this means in particular that with probability 1, if you look at the zero set of this object, this zero set is given by a union of disjoint, smooth, closed curves that are represented here. So this picture on the right is just a zoom of the picture, just an enlargement of the picture of some region of the picture on the left. And in this picture, we see several colors and points and lines. So the black lines here are the zero set of your Berry random wave model, of one realization of the Berry random wave model, which is called the nodal set. So this is a collection of smooth rectifiable curves, and you can actually measure the length of these curves. And then there are two colors. The green color corresponds to the region where the Berry random wave model is negative, and the white where the Berry random wave model is positive. And then there is a lot of dots So the blue dots are the minima, the red dots are, the red dots are the minima, the blue dots are the maxima, and then the black dots are the saddle points. Okay, they're the critical points. So this is a random set, a random collection of curves, and a random collection of regions. So what you can do when you have an object of this type, what are the typical quantities that people are interested in? So first of all, you can look at global quantities. These are typically very difficult to study. The global quantities, for instance, you can count in this square, on this big square, the number of connected components of the green set, so the negative excursions. So this is a very difficult object to study, and it's a global object. There is no way to reconstruct the number of connected components of the green set by first looking at the tiny square here, and then looking at the same object in the tiny square here, and then try to glue things together. Already here, we do not know if this green line and this the green region and green region are connected or not. So we cannot look locally at what happens and hope to reconstruct everything. So another quantity people are interested in is, for instance, is the event that this set percolates. So meaning that you can go from the east side of the square to the west side of the square by just crossing green regions, for instance, or white regions. So this is another very difficult question. And then there are objects that are more amenable to analysis by our techniques that are local quantities. So for instance, you can ask yourself, what can I say about the distribution of the area of the green region? Okay, this is a local quantity. You can measure the green region here, 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 and then glue things together. And then there is something which is slightly more complicated because it refers to a lower dimensional set. You can measure the length of the nodal set. That is the length of the black lines that are represented here. This is exactly what you're interested in, right? So we would like to understand, so we fix a region, Q, like this unit square here. And then we measure the length of the black lines, the length of the nodal set of the very random wave model, and we let E go to infinity. Now, if this fact of fixing a region, letting E go to infinity is a bit maybe uninteresting, of course, if you look at the shape of the covariance function here, you can easily re-express this problem into the problem of looking at the length of a nodal set for one fixed E, like E equal to 1 over growing regions. Okay, you can re-express this problem by fixing the eigenvalue and letting the region grow, and up to a renormalization of some constant, the problem is exactly the same. Okay, but this is more connected to the same. Now, okay, so this is our interest, is the length that is here. Now, this quantity, this random quantity, is a random closed set, and we are measuring it, and was studied in a very remarkable paper of 2002, always by Michael Berry from Bristol. And he did what anyone would do, started by computing the expectation of the set, and then the variance of the set, right? And so the expectation of the set can be easily computed by using a tool which is known as the Katzreis formula. And this is equal to the square root of E. And it's a direct computation. And then you can do, and then what he did is that, okay, now by using some heuristic arguments that are related to the specific shape of what is in this Katzreis formula, one can guess an order for the variance, right? And the order for the variance that he guessed in the first part of the paper was square root of E. Okay, if you look into the computation, you realize that this is a perfectly legitimate guess for the order of the variance. And then what happens is that he realized at a certain point that many of the terms that would have contributed to the leading term of this guess for the variance were already simplifying at the limit. And actually, the exact order of the variance is the logarithm of E. Okay, so it's much, much smaller than was observed before, right? So there is a legitimate guess for the variance, and there is some cancellation going on into the terms that would give the leading term of the variance that make that the variance is actually a logarithmic rate at infinity for E going to infinity. And what he says in this paper is that this variance reduction results from a cancellation. It was obscure in 2002, and then it's been clarified in many ways later on. Okay, so I actually spoke with Barry visiting Luxembourg and told him this paper, and it was like, oh, I thought everyone had forgot about it, but I'm happy that people are still looking into this phenomenon of cancellation. And then, of course, you can do the same operation in other frameworks. So another framework where this cancellation was done is on the sphere. So you take a sphere, and you take the equivalent of this very random wave model of the field, which is a model of random spherical harmonics. So I mean, spherical harmonics are orthogonal functions, orthogonal eigenfunction of a Laplace operator on the sphere, and you can build Gaussian version of them, And here the eigenvalues are this n times n plus 1, n of unit minus here, depending on how you look at eigenvalues. And you can exactly play the same game. You can generate those on the sphere. So the black areas are the negative excursion, the white areas are the positive excursions, and then the boundary between them is a nodal set. You can measure it. And what Igor Wigman proved in 2010 is that there is the same cancellation. And so there is an order, which is the legitimate guess. Terms simplify exactly. And at the end, you have a logarithmic increase, a logarithmic rate for the values, right? Now, there is another interesting model that where this, so there is the same kind of cancellation phenomenon. And so there is another model, which is a model of random eigenfunction with a Laplace operator on the torus. Okay, and let me describe this. So you start with two-dimensional torus, which you can visualize as the interval 0, 1, I mean the square 0, 1 to the power 2 with opposing sides that are glued together, right? And you can look at eigenfunction of the Laplace operator, random eigenfunction. First of all, eigenfunction with Laplace operator on this space. So we are looking for random, possibly eigenfunction of the Laplace operator on this space. Now, what happens is that you can identify functions on the torus with canonically identified with function on the plane that are one periodic in each variable, meaning that it's quite easy to show that an L2 complete orthonormal set of eigenfunction of delta is given by this complex exponential. So it's a mapping like the exponential of 2i pi lambda 1 x1 plus lambda 2 x2, where lambda 1, lambda 2 are integers, right? And each one of these eigenfunctions is associated with the eigenvalue 4 pi square, lambda 1 square plus lambda 2 square, okay? So this means that all the eigenvalue of a Laplace operator on the torus have the form of 4 pi, which is not really particularly significant, plus the sum of 2 squares, okay? So, in particular, the set of eigenvalues of the Laplace operator on the torus are object of the form 4 pi squares times n, where n is an integer that can be represented as the sum of 2 squares. And this is a set which is very thin within all integers. It is density 0. There are very few of them. For instance, 5 can be represented as the sum of 2 squares, and 6 cannot, and etc. So there are many of them that are not covered. And the size, and of course, it's quite easy to realize that the size of the eigenspace, which is associated with the eigenvalue 4 pi square over n, corresponds exactly to the number of ways in which you can represent a given integer as a sum of 2 squares, where the order counts. So you can, 5 is 1 plus 2 to the power 2, and 2 to the power 2 plus 1, and then minus 2 to the power 2, etc. So there is. And so I'm going to denote this, this size of the eigenspace by this nn. So there are several notations that are used in the literature, so I'm going to choose this n of little n. And this is quite a classical object in number theory. So for instance, we know that R2 of n, so this number here, is negligible with respect to any positive power of n. And actually, we also know that on average, you should think about this number as something like the square root of log n. So it's a very, very slowly increasing number. And also, we know that there are pathological behaviors that are possible. That is, there is sequences of prime numbers such that this guy is always equal to 8, okay? So we really have to assume that this number R2 of n is going to, so we're going to assume in the following that this number is exploding to infinity, right? And now, what is an arithmetic random wave? So this arithmetic random wave is a random eigenfunction of a Laplace operator. Is obtained as follows. So there is a normalizing factor. So you fix a number n that can be represented as a sum of 2 squares. Then there is a normalizing factor. And then you take the sum over all vectors lambda that decompose n as a sum of 2 squares. You take the corresponding exponential and multiply it by complex vector, Gaussian vector. So the A lambda are IID complex Gaussian vectors, except for the requirement that A of lambda is equal to the conjugate of A of minus lambda, in such a way that this guy here becomes a real valued function. All complex parts simplify, and this becomes. So this guy is a very interesting collection of random fields, and it is stationary. It is invariant with respect to translations. And once again, one is interested in the behavior of the total nodal length of this guy. So you fix the torus, and you have the zero set is given by a smooth collection of curves that are rectifiable, you can measure them, and you can then look at what happens whenever you let n go to infinity, right? Whenever you let n go to infinity. So some remarks here is that, so this guy is a stationary Gaussian process, and there is at least one interesting phenomenon that goes on, and the phenomenon is the following. So you can express quite easily the covariance, so if you look now at the covariance between fn of x and fn of y. So typically, for stationary processes, you can express the covariance in terms of a spectral measure. This is the Fourier transform of a given probability measure. And the given probability measure that appears here is obtained, can be represented in terms of a probability measure on the sphere, on the unit circle. Look at here. We are looking here at points, integer point lambda, that stay on the circle of radius square root of n. Now, if you multiply them by 1 over the square root of n, what you obtain is a collection of points on the unit circle. And they generate a probability measure on the unit circle, which is given by mu of n. And this mu of n is the spectral probability measure associated with this stationary process. Now, what happens typically when you look at Gaussian fields, for instance, look at the Gaussian field that appear in this book by Adler, is that if you look at some limit, the spectral measure of these fields is converging to a limiting spectral measure. So there is a unique measure that is the limit, a weak limit, for instance, the spectral measures of your fields. And what happens here is that this is not the case. Due to the very strong arithmetic flavor of what you are doing, this set of spectral measures is an infinite strict subset of the class of invariant measures on the circle, invariant with respect to these two operations here, and there does not exist a unique weak limit. And this you can actually appreciate it quite easily if you compute the fourth Fourier coefficient, which is done in this paper by Krishnapur, Kuhlberg, and Wigman. And so this is the fourth Fourier coefficient of this measure here. If this measure mu of n had a unique limit, then this numerical sequence would converge to a unique value, to a unique number. But actually, all the possible limiting values of this quantity are given by the whole interval 0, 1. And so this explains in particular, this shows in particular that this sequence of spectral measures do not have a unique limit. Okay, so to resume, we are constructing a random eigenfunction with a Laplace operator on the torus, and what we have is that the limit of the corresponding spectral measures depend on the choice of the subsequence within the set S of integers that can be represented as a sum of squares. Okay, as a sum of two squares. And we are looking at the asymptotic behavior of the zero set, of the length of the zero set of the torus of this object. Now, so the first paper that studied this quantity, so the length of the zero set, was a paper by Rudnick and Wigman. What they proved is that the expectation is exactly as the expectation computed by Berry, up to some normalization. And then they conjectured, so they computed some upper bounds. They conjectured that the variance of this set, of the length of the nodal set, was of the form E of n, where E of n is the eigenvalue divided by the size of the eigenspace, right? And then, of course, everything is, proving actual asymptotic equivalences for variance is a very difficult business. And what actually they proved is that this conjecture was too conservative. And indeed, the variance is of the order, the eigenvalue divided by the square of the size of the eigenspace. So something which is much smaller, multiplied by correction factor that depends on exactly this fourth Fourier coefficient. So this means in particular that the tiny fluctuations of the variance in the leading term depend on the choice of the subsequence. So depending on the choice of the subsequence, the value of this constant can vary, and actually can vary between 1 over 512 up to 1 over 256, right? And okay, there is one key point in this proof is that there is a rest which is expressed as the power of a fifth integral of this that has to be shown to be negligible, and this is a very, very difficult problem, arithmetic problem. So there is a proof by Bombieri, Bourgain, and so here there are two phenomena. Then again, there is a phenomenon of cancellation. The conjecture variance is actually much smaller. The true variance is much smaller than the conjecture one. Again, the leading term. And then there is a non-universality in the sense that there is a tiny correction term that depends on the choice of the subsequence, right? So we would like to understand. So a little bit of entertainment. So this is a physical representation of zero sets. This is the first time that zero sets of eigenfunction with Laplace operator was observed. This is a reproduction of of an experiment by a violinist and physicist Chladni, a German one, in 1787. So what he did, he took a plate, put sand on the plate, and then excited the plate with the bow of the violin. And he observed that the sand formed very nice patterns that are known as Chladni patterns. And these patterns correspond to the zero set, correspond to the point where the plate is stationary. And this is actually the zero set in this specific case of the bi-Laplacian, so it's the iteration of a Laplacian, but you can also generate zero set for Laplace operator like this. Okay, so this is a zero set. These are the Chladni plates that appear. Okay, and of course now we are interested in the very typical question. We're interested in a very typical question for this community is that we have now exact asymptotic for the variance and exact expression for the mean. What can we say about a second order result for these quantities? And so in particular, so we are looking at this normalized and centered version of the nodal length, both for the case of the Berry random wave model and for the arithmetic random wave model. And we would like to understand what is the nature of the limiting random variable that appear. So of course, in this arithmetic random wave model, we have a non-universality behind. So the defined behavior of the variance depends on the choice of the subsequence. And of course, since we are normalizing and centering, if the limit here z was Gaussian, then we would lose the non-universality in the second order limit. So there is an underlying question here that the question is that, is the limit in the arithmetic case Gaussian or not? Meaning that, can we see the non-universality in the limit that you observe on the variance, which is not the case. And here, and then what happens is that, and this is the connection with the first part of the talk, is that this kind of questions, and also the cancellation phenomena that were observed by Berry and also in the other reference here, are all related to the same phenomenon, which is the following. So first of all, in any case, you can always represent the length of a given nodal set in this form. This is an application of the co-area formula. And what it means here is that, so this is the Dirac mass at 0. And so this means that here I replace the Dirac mass by some approximation of the Dirac mass, and then, for instance, by the Gaussian density with the variance conversion to 0. And then this quantity converges in L2 to something, and this something is exactly the definition of this integral here. Once you write things in this form, then you can write quite easily a Wiener chaos expansion for this by formally expanding the Dirac mass into Hermite polynomials, and by using the fact that by stationarity, at any given point, the field and the gradient are independent, so you can work with this and quite easily write a Wiener chaos expansion. And what happens in all these examples of the nodal set is that so by reasons of symmetries, you know already that all odd Wiener chaoses are going to be 0. And there is no reason a priori to expect that a given even order Wiener chaos would be equal to 0. But what happens is that since the eigenfunction we are looking at are eigenfunction of a Laplace operator, there is a very nice and surprising analytical, pathwise omega by omega cancellation that makes that the projection on the second Wiener chaos is exactly equal to 0. Meaning that the first leading term in this expansion is always given by the fourth chaos. And all the guesses for the variances that have been done in the literature before proving exact asymptotics for the variance comes from the fact that these are right guesses for the projection on the second chaos, which actually disappears. And so this cancellation phenomenon is actually a cancellation of the first chaos. And what happens indeed is that in the limit, there is just one chaos that survives. Everything else is killed by the variance and is exactly the projection on the fourth chaos in all these models. Meaning that the asymptotic behavior of this nodal lengths actually inherit completely the rigid asymptotic structure of the Wiener chaos and the underlying Wiener chaos that I was describing at the beginning. Okay? And then once you have the projection in the surviving term, you have to study it by Bayer-Hansen, depending on the model. And so the result we have are the following. So first of all, let's look at the Berry random wave model on the plane. So we know already that this projection on odd chaoses is going to disappear. And what happens is that also the projection on the second chaos reduces by simplification, which is due exactly to the fact that these guys are eigenfunction of a Laplace operator to a negligible term, in such a way that the fourth chaos is exactly the chaos that dominates at the limit, right? So that you can study this fluctuation by using, for instance, this bound, if you guess that there is a Gaussian simplification. And this is what we did. We applied this kind of bound, we expressed in monoanalytical terms. and prove that the Berry random wave model verifies the central limit theorem. So the length of the nodal set of Berry random wave model verifies the central limit theorem, and the cancellation phenomenon observed by Berry is due to the fact that the second chaos disappears because the random eigenfunction is actually an eigenfunction of the Laplace operator. Now the second result is that we are looking for arithmetic random waves. I know this is not important for this discussion, it goes as follows. So what happens now is that, so you have no boundary, and so the projection on the second chaos actually disappears completely, because the term that gives you, the negligible terms appearing in the Berry random wave model is the boundary term that disappears on the torus. So once again, the projection on chaoses of odd order plus the projection on order 2 disappears. And then the leading term is exactly once again given by the projection on the fourth chaos. And now the interesting thing that happens is that we can actually recover non-universality at the limit because the limit is non-Gaussian. Okay, so on the torus the limit is non-Gaussian. It is actually a combination of center chi-squares, which makes the look for bounds in the chi-square approximation relevant even in this domain. And what happens is that now if you look at the length and assume that you are going to infinity following a sequence such that the absolute value of the fourth Fourier coefficient converges to some number eta, right? And we know from my discussion before that this number can be anywhere between 0 and 1. Right? You can choose a sequence and realize any of these numbers. Then this nodal length is converged to a linear combination of chi-squares independent whose coefficients depend on the value of eta. Right? And in the most common, in the case which is the one that, in the dominant case, meaning that most of the, in an informal way, most of the subsequence you can choose will converge to the uniform measure on the circle, meaning that this eta is going to be 0. Okay, so the most represented case is the case where eta is equal to 0, and in this case, this is just a minus, it's just a multiple of a chi-square, center chi-square with 2 degrees of freedom. Right? Okay, so this appears. And you can read the non-universality in this framework. And so I know that I'm out of time, so what I would like to tell you is that via Stein's method, we have an exact control, at least in the Wasserstein distance, of what's going to happen. And the reason why we choose the Wasserstein distance is quite easy to understand, because we know that our object is the sum of a dominating term plus something that converges to 0 in L2, which tells you that the Wasserstein distance can be dominated by the Wasserstein distance between the Gaussian and the dominating term plus the L2 norm of the residual. And there is a technical point that I don't have the time to explain, is that the fact that delta 0 at the beginning, so we start with a representation of our objects that involve a generalized function, which is not an element of L2, creates a number of technical problems, because there are series that are not converging, and we would like them to converge. And okay, and I think that I can just thank you for your attention. Thank you very much.